Remember, the nuclear membrane is a phospholipid bilayer. The endoplasmic reticulum is a phospholipid bilayer. These transport vesicles are phospholipid bilayers. The Golgi apparatus is a phospholipid bilayer, and the secretory vesicles are phospholipid bilayers, and the cell membrane is a phospholipid bilayer. Any cell that has this cellular machinery is able to replenish its cell membrane via this process. So this is why red blood cells will only last maybe 120 days, because we basically, as they become mature, we spit out all of their cellular machinery, so all we're left with are these carrying molecules, the oxygen carrying molecules we call hemoglobin. So now, because there's no way to replenish the cell membrane, those cells will only last for maybe 120 days. And as they travel through the bloodstream, they become more fragile or friable because we slough off some of these phospholipids over a period of time. We slough off enough of them, that cell doesn't have enough, it's got too much tension on that cell membrane, and eventually it will burst. Where does it typically happen? Either the spleen or the liver. So, let's back up again, talk about this. Because the question is always asked, well, by the time we go from the endoplasmic reticulum to the Golgi apparatus, have all these molecules transitioned from the pre-pro hormone to the pro hormone? And the answer is, and don't write this down, just think about this in general, this concept. The answer is no. Okay? It's not that clear cut. This is not like an assembly line. We go from one area to the next area, and we've got complete conversion between those two areas. It doesn't happen here. What we do know is that you've got enzymes that are made right here, right? Enzymes that are made right here. And this is just kind of a continuous process of chewing up these little proteins with the enzymes that are involved. So we'll say, in general, what will happen is that most of the pre-pro hormones have been digested into pro-hormones by the time we get here, but not all of them. We could have some pre-pro hormones still at this level. How many? Maybe 5-10%. Okay, and by the time we get over here, are we Are we secreting 100% active hormone? What do you think? No. This is not that cut and dry. We're probably secreting maybe 95% active hormone. But I just want you to understand, it's just kind of a continuous digestive process as we move from the ER to the Golgi apparatus and then finally to being released outside the body. Any questions? And to give you an example, since we're dealing with, it can be a protein hormone that starts this. But what's happening is we're initiating transcription and translation within the cell. Okay, it could be a steroid, it could be a protein, but let's go steroid instead. I think steroid's probably better. But we want to make some type of protein, so we're going to start inside that cell. Remember, we've got a hormone. Did we talk about hormone response elements in here? Yes. We did, didn't we? Mm-hmm. Hormone response element is what this steroid hormone receptor complex binds to. And then it'll start to make our mRNA, our messenger RNA, within the nucleus. That messenger RNA comes out of the nuclear pore, out of the nuclear pore, and of course it's going to bind eventually to these ribosomes. Now the ribosomes can be in the cytoplasm, or they can also be bound, but a lot of times, we'll see a mixture of both of those. But what happens, the mRNA then will bind to that ribosome, and there's a heavy and a light subunit, right? You can see the lower subunit right there. This is the ribosome. The lower subunit is the heavy subunit in this case, and then the upper one is going to be the light subunit. Now there's an enzyme, and I alluded to this before, I said it before, but there's an enzyme known as tRNA synthetase. And its job is to basically bind, okay, we're just going to call this a tRNA, I'll put a T up there. It's going to bind an amino acid, AA, to the tRNA. Okay? And you all know what that structure looks like. It kind of looks like this. Right? You've seen these before. So it binds the amino acid to the tRNA. And that's the molecule that does it. It says that in the notes. Like on the next page, I think you've got the whole list of what happens here. Don't you? Next page. What you got there, So you got a list of 1 through 8 there. That should be everything I'm talking about right now. So the amino-sealed tRNA synthetase binds the amino acid to the tRNA. And of course, the tRNA is what allows us to come down in here, bind within the ribosome to start to make that protein. Okay, so I don't know if you've got the same picture there. Yes. So then what happens? We got our original amino acid, protein is being built here. Another enzyme comes in here to bind this protein on the existing protein strand because we're building one, and make this polypeptide bond in here. And that's called peptidyl transferase, and that's on the next page. Peptidyl transferase binds the new amino acid to the existing protein strand. So as it says, I think in the notes there, it says something about growing the protein. This is the way it works. So the next thing you've got, next thing we want to identify is this signal peptide. Okay? This signal peptide is there. That's the first amino acid sequence in this protein strand, is the signal peptide. Now remember we talked about pre-pro hormone last time, remember that? We'll call it a pre-pro hormone if it still has that signal peptide attached to it. Once we remove the signal peptide, we're just going to call it a prohormone. Now why is the signal peptide there? Well, it's got a little attachment site for another structure known as the signal recognition particle, which is this dude right here, SRP, signal recognition particle. And those are found within the cytoplasm. Via diffusion, they'll eventually bind to that signal peptide right here, bind the signal peptide, and then that whole complex. Now, look at the way I've got this drawing here. The signal recognition particle and the signal peptide, they come in together, and they'll bind to this little channel, we'll call this a channel. I'll give you a correct term for it in a minute. But it binds to this channel here in the endoplasmic reticulum. That channel is called a translocon. Does that sound familiar to anybody? A couple people? This channel right here is known as a translocon. So the signal peptide is made first, the signal recognition particle binds to it, and they all come down together, and then that signal recognition particle basically binds to a receptor site on the translocon. As I said, all this is pretty much found on that next page in 1 through 8. Right, Ms. Chafin, is that right? You see that in there? What I'm saying? So then what happens, the function of this whole, this combination of molecules allows us to guide that protein molecule into the endoplasmic reticulum. Now this is a rough ER, so that means we're going to be making what? Proteins. So once again, and I've just got a short one here, but of course you know these would be much longer than this. The mRNA travels through here, and as it does, it builds that protein molecule, and it comes into the endoplasmic reticulum, and we go to then the next step in this process. And that is the building of this protein. And two things basically happen here to cause the folding of the protein in the proper configuration. We see disulfide bond formation. Disulfide bond formation to cross-link the proteins at the proper locations to provide that proper configuration. Disulfide bond formation. And the other thing we see too is N-glycosylation. So we add sugars onto these proteins, and that's what you can see that's happening down here. Okay? So we go from the endoplasmic reticulum. You can see right here we're seeing Golgi apparatus. So let's back up for a second. we have a transport protein that transports this entire structure, and we already covered this too, didn't we? Transport protein to the Golgi apparatus. There's a little enzymatic reaction that's occurring there. And then we get the Golgi apparatus. Not only do we see the N-glycosylation and disulfide bond formation, we also have enzymes that will chop these things up into smaller parts to make them or prepare them to become active. And then, of course, the last thing we have is the secretory vesicle. So we got transport vesicle between the ER and the Golgi. We got a secretory vesicle between the Golgi and the cell membrane. So this is cell membrane, cell membrane right here, phospholipid bilayer. And we're going to secrete that vesicle, allow it to bind to the cell membrane to release those hormones outside this, no, not hormones, proteins outside the cell. You'll write about, somewhere about in here. So then we end up with this molecule down below, okay, everything from here over, and that's what insulin looks like. And then this structure right here has really no known effect. It's called a C-peptide because of its C-peptide because of its shape. So you have that in your notes too, don't you? What is next? No? Oh, well, sorry about that. So what about this? Do you have this at all in there? No? All right, so you can draw this. I just kind of covered it. You don't have to draw these other pictures. You can just slice it where I did. But you see the pro-insulin here with the disulfide bonds, disulfide bond, disulfide bond, disulfide bond. And then what this does, it kind of bridges. You'll see it a little later on when we look at the receptor tyrosine kinase molecule that this binds to, the receptor site for insulin. It bridges over the top of these two beta subunits, alpha subunits, and initiates the activity of insulin within the cell. And we'll learn about all the stuff that insulin does later on. Did I say what the anabolic hormones in the body were? You mentioned that in here already?
Yes, the 5.
Yeah, so
Thyroid.
what did we say again? We said testosterone,
Right, thyroid.
HGH, thyroid, IGFs,
And,
what? And insulin, that's right.
insulin, yeah.
So there's 5 of them. I'll say them again. HGH, IGFs, thyroid, testosterone, and insulin. So those are all anabolic hormones. And the reason why we say insulin is, you'll probably hear me say this later on this semester, but the reason why we say insulin is not because it brings sugar into the cells. It does. Helps to allows us to have a currency for energy, right? But it also brings proteins into the cells. It is highly anabolic. But what I always like to say, you know, if you're looking at the bodybuilding world, bodybuilders have this mentality, if a little bit's good, then a lot's got to be better. And you can't do that with insulin. A lot of insulin's going to kill you. If you don't have enough insulin, you get something called a diabetic coma. And that'll eventually kill you if you don't get it fixed. If you take too much insulin, you end up with something called insulin shock, and that happens pretty quickly. If you don't rectify that problem, the patient will die. And there are probably, I would say there's speculation of about 4 to 5 elite level to pro level bodybuilders, professional elite level bodybuilders that have died from insulin overdose. They didn't need it, they weren't diabetic, they took too much of it, and it killed them. Okay. Adrenal gland cells all can make this. So we're going to start our drawing from the top. What you have up there is an LDL. Do you see that? That's a low-density lipoprotein. That low-density lipoprotein has a lot of cholesterol in it. Got some triglycerides in there, but a lot of cholesterol in this LDL, low-density lipoprotein. Liver has these too. Liver has these receptors.